Yeah, let's restart. Yeah, let's have a brief overview of what we covered in the last lecture. So we have 3 topics. First is QAM, and second is applications of amplitude modulation, and last one is angle modulation. Okay, so so this class focuses more on the analog communication. So one reason is that, yeah, no matter what you're talking about, the digital communication, for the transmission part is always analog, right? There's no way to transmit digits over the air, right? Everything's analog. Okay, for example, for the QAM, right? So we see, we see there's one application that uses QAM for analog TV, right? But in the digital communication, so we use QAM all the time, right? QAM is the only thing, almost the only thing we use for the digital communication, right? Okay, so analog communication is very important. A lot of concepts here can be borrowed when we talk about the digital communication, okay? So yeah, the angle modulation is the last part of the analog communication. So although we just have one topic here, but this is a huge topic, right? So analog communication is 1 times 100 more complicated than amplitude modulation, right? So we're going to see what we're going to cover there. Okay, so for the QAM, let's review the motivation here. So basically, the reason we want QAM is that we still want good bandwidth efficiency, like single sideband communication, right? Meanwhile, we do not want the Hilbert transform that we need for the single sideband communication. Okay, so basically, the solution here is that, you know, in order to use the part of the Hilbert transformation to cancel half of the signal. So basically, we transmit another signal, right? So that's the basic motivation for the QAM, right? Basically, if you see the modulation structure, it is extremely similar to the single band modulation, right? The only difference here is that we don't have a Hilbert transformation here, right? So basically, what we have here is another signal, right? So we transmit signal in the same 2 signals in the same time. So for this part, it's just nothing but the DSBSC, right? And this we just use another signal multiplied sine, right? And then we add them together, and then we transmit, right? So the decoding or the demodulation is very straightforward, right? So basically, what we do is that we just use a cosine, multiply this by a cosine to demodulate this, and multiply this with a sine to demodulate with that, right? So the procedure is not very complicated, but what is the fundamental reason that we can do the demodulation is that, so the M1 multiply cosine and M2 multiply sine, these 2 signals are orthogonal, right? So we derive it and show why these 2 are orthogonal. So that's the fundamental reason why it works, okay? And the other thing that is very nice is that because of this structure, so it basically means that, you know, because of the fundamental nature of cosine and sine, so we can transmit 2 signals and at the same time, right? So we're not, so we didn't see it here, but we're going to see in the later that, so this is extremely important for the digital communication. Okay, so basically we can imagine this guy as a real part of a complex number, and this guy as an imaginary part of a complex number. And then it means that we can transmit a complex signal equivalently, right? Because of this, okay? But we're going to see that many lectures later. Okay, and this is how it works. And as I said, so QAM have been used in the analog TV. And for the digital communication, you can see it has a huge use here, right? For 4G, 5G, LTE, Wi-Fi, cable modem, DSL, whatever. Yeah, I think most of the communication technology using QAM for transmission because of its high efficiency and simple demodulation. Okay, very important for digital. Yeah. Yeah, and then we went through 3 applications of amplitude modulation. The first application is AM broadcast radio, right? And anybody check it in the 75, I think? So did you check whether there's like 4 antenna base station there? So if you haven't, probably you want to check it in the 75, Southwest 75, and Southwest 8th Avenue. Yeah, maybe you can take a look at, we have a big AM 4 antenna base station there, okay? Yeah, and I will not cover that again. So basically, you can watch the video when I upload it. So if you haven't for the analog TV, so this is a very interesting example, right? So we have every modulation for the for this one, it's just AM, right? But for the analog TV, so we have QAM, we have USB, we have LSB, but we'll use that in the VSB fashion, right? Because we want a lower order filter to do that, right? And yeah, so those are the signal, how the signal look like in the frequency domain. So we need to transmit the audio separately, and those are the video component, right? And the black one here is the luminance information, and the red one here are the color information. For each of them, so we use QAM, and on top of QAM, we use VSB transmission, right? And for the VSB, we use both upper sideband and lower sideband for efficiency, right? So this is kind of very nice example. We want to go over that a little bit more. And then the other thing we talk about is long distance telephony. So basically, yeah, here I think the important concept we want to cover here is, so first of all, it uses SSB for signaling, right? So important concept I want to cover here is a frequency division multiplexing, right? So basically, each signal is transmitted in each frequency component, right? So basically, for each of this band, I think the width of the band is 4 kilohertz, right? Yeah, the band is 4 kilohertz, right? And then we just, we have non-overlaps this kind of signals, right, to transmit, right? In the frequency, so all the signal will transmit in the same time, but in the frequency domain, so they are not overlapping, right? They're still like orthogonal kind of communication, okay? Okay, very good, and yeah. And then we just started talking about angle modulation, and first for the motivation is that for amplitude modulation, so one big disadvantage is that the noise is directly added on the signal itself, right? And we use the amplitude to carry the information, but the noise is added directly on the amplitude. So it kind of intuitively, it may have a big impact on that, right? So in order to solve this kind of problem, then we still want to modify the carrier, right? How we modify the carrier is to, modulate the carrier another way, right? The way that we're going to do that is modify either the frequency or the phase, okay? And both of them are called angle modulation, okay? And another nice property of this kind of modulation we want is this one. We didn't emphasize that a lot, but this is a fact, right? So basically, what we want is that if a signal has more bandwidth, so we want to have more signal-to-noise ratio, right? So basically, the signal-to-noise ratio is defined as the signal power divided by the noise power, right? You can imagine if that is bigger, then the quality of the signal would be better, right? If there's no noise, so that's the ideal case, right? So basically, that's one of the most important metric in wireless communication. Okay, and for the FM, and so we definitely have this kind of very nice property, right? And the disadvantage here is that for the modulation, so there's some advantage, but the disadvantage is that so the demodulation is not easy, right? Because the changing is over the frequency or the phase, right? How can you demodulate it, right? That can be harder in practice, and because it's harder, then we're going to spend lots of time on that. So basically, we're going to cover the phase lock loop here in detail, right? Because that's how we do the demodulation, and also an side effect is that so the phase lock loop will also give us the carrier, the exact carrier with very small phase difference. Okay, as we said, right? For DSB-SC, so we don't have the carrier transmitted, right? For AM we do, but for DSB-SC we don't have it. But we don't want to generate. I mean, we cannot generate it locally without, the phase difference, right? And we just mentioned that before. So phase lock loop is a way to do that, and we're going to see how we do that in detail. Okay, we're going to spend lots of time on this. So, okay, and here are some notation that I want to introduce. So basically, oh, I missed an equal sign here. So, yeah, this basically means angle, and so this is a modulated signal, right? So st equals to a times cosine theta t, right? Those are equal sign here. I'll fix it. Okay, and another important thing here is that so theta here is the definition of the phase of this cosine, right? And the frequency is nothing but the derivative of the phase, right? Why is that? Because the phase is how much change up to time t, right? For the angle. Okay, then frequency means how fast this change is, right? It's like, okay, accumulatively now we have theta t, and then what would be the omega, right? So this is a kind of the definition of the derivative and the integral, right? So basically, yeah, this is the relationship between the phase and frequency, right? Do a derivative to get a phase. And another thing is that, okay, so the frequency can vary also with time, right? I think in the previous slide, the frequency is now changing with time because we consider this a linear frequency, omega c times t, right? Yeah, you can write here as omega c, right? Doesn't matter. So yeah, in this case, right? So basically, you can get omega will not change over time, but in practice, omega will change over time because we want to modulate our signal on the frequency, right? Frequency will be changing over time. So basically, in practice, omega will be a function of t as well, right? So we denote that as omega I t. And to indicate it's an instantaneous frequency, okay? Yeah, we didn't cover the last slide in the last lecture. We just briefly mentioned it here. All right, any questions? Okay, so let's continue. This is our lecture number 18, and today we're going to cover, so basically our last topic is angle modulation. Okay, so here we have 4 topics to cover in total. Of course, we're not going to go over all of them today, so let's see how many we can go. The first one is an introduction, so we're going to introduce a basic concept of the angle modulation. And second topic is the properties of angle modulation, such as, so whether this modulation is linear or not, right? We may imagine that the AM modulation may be linear, right? See whether that is a linear modulation or not, and the SBSC, right? And so what is the power of the signal, and what is the bandwidth of the modulated signal, right? So we want to investigate a few properties of the modulated signal, and then we're going to talk about the modulation part. Okay, and here for the modulation, we'll focus on the FM signal, right? Because this is mostly used for the analog communication, right? So for the PM, we use a lot on the digital communication. And then we're going to talk about the demodulation. Okay, and also we're going to focus on the FM, right? So that's the agenda for the angle modulation. So probably we're going to cover the first 2 and touch a little bit on modulation, hopefully. Okay, today, great. So let's talk about the first one, right? The introduction. Okay, so we just mentioned that the frequency is the derivative of the phase, right? So let's remember that. So omega I of t equals to the derivative of theta t. Okay, very nice. And then, so as we mentioned, right? So for the angle modulation, we have 2 types of angle modulation. Okay, so we have 2 basic types of angle modulation. Okay, the first one is FM, is the phase modulation, PM. Okay, and second one is the frequency modulation. Or call that FM. Okay, by the way, so yeah, when we say why we want the angle modulation, we say this can be better, right, compared to AM modulation. So you can hear it from the radio, right? So when you listen AM radio or FM radio, there's a huge quality difference. So FM is way better compared to AM, based on my experience. So, okay, so now let's see how we do the phase modulation, right? So we're going to see how we can do that mathematically in terms of mathematical expressions, right? That's always easier. And then we're going to see how we implement that in practice, right? Okay, for the phase modulation PM, so for this one, we see the angle theta t will vary linearly with the message signal mt, right? So this guy is varied linearly with our signal mt, right? So the key here is linearly, right? So what does linearly mean, right? It means the following. So basically, our phase theta t will equals to our carrier frequency omega ct multiply a constant here, we call that kp, and then multiply mt, right? That will be our angle, right? Does that make sense? So basically, it basically means that, yeah, let's see, say if our st equals to cosine theta t, right? It means that the angle here carries the information mt. Okay, if we ignore the carrier frequency, right? So this theta t will be just equal to some scalar times our message signal, right? So the change of the angle means that represent our message, right? That makes sense? Okay, so this is the idea. Okay, so for some unit, so here, if we write omega here, so basically we're in radians, right? And the constant here, so we're going to see many constants here in the angle modulation, right? They're all kp or k, whatever, something else, right? Because everything here when we do, so we need some sensitivity there, right? Because in practice, we need to use a mechanism to change the angle. Right, so when we change the angle, it will not be exactly mt, right? There will be some sensitivity vector here, right? So this kp, so it's called the phase sensitivity. Okay, and the unit of kp is what? Right here should be radians times second, right? And we know here, this guy, usually, let's say the message signal is in terms of volts. And then, so this would be what? Yeah, so the unit of that is radian per volt, right? This volt has to be canceled with this. Right? Let's say this is volt multiplied second. Okay, and that is the unit of it. So therefore, we can write down, so using this formula, this is our modulation formula. So we can write down as PMT equals to cosine. Just put the theta here, right? So that's omega c t plus kp mt. Okay, so that will be the modulated signal. Okay. Very nice. Any questions so far? Yeah, straightforward, right? And from here, we can compute the frequency of the angle, right? So basically, the frequency of the modulated signal, right? So basically, omega it, so that's equals to this guy, right? The derivative of our phase of our angle, right? So that equals to d theta dt, right? And what does that equal to? For the first part, we do the derivative of this linear part. We got omega c, right? Then we add kp and the derivative of mt, right? Right. So that's basically the frequency of the transmitted signal, right? And we can see here the frequency is definitely changing for this transmitted signal. Okay. Okay. So this is in. So if we write it this way, so that's in radians, right? And if in hertz, so this guy will equals to, we divide everything by 2 pi, right? Because omega c equals to 2 pi fc, so that will be fc plus kp over 2 pi. And then we add this derivative, okay? Yeah, any questions? Great. And then let's talk about FM. Right? And let's compare the difference between these two, right? And for FM, so the concept is very similar to this, but the only difference here is that, so there we say theta t is varied linearly with mt, right? So in contrast, here we say the instantaneous frequency right? So basically, it means that the omega it, right? So instantaneous frequency means omega it. So that is varied linearly with mt, right? The frequency is varied linearly with mt. Therefore, it basically means that in contrast to the theta t there, so here we have omega I of t equals to what? The omega c, which is the carrier frequency, plus a constant, we call that pf here, and times mt, right? And similarly, kf here, so that's called frequency sensitivity. Okay, and who can tell me the unit of it? Yeah, let's say given the unit of kp is radian per volt, right? Then what's the unit for this guy? Exactly. Very nice. It's a radians per second per volt, right? Because now we're talking about the frequency. Okay, we need to divide it by t. Okay, and let's see. And this guy, if we write it this way, it's in radians, right? And similarly, in hertz. So what we got is FIT equals to, so we divide this guy, everything by 2 pi. It's FC plus KF over 2 pi MT. Okay, and that's how it works, right? If you compare those two, yeah, they're very similar, right? But here, the angle carries the information, but here the frequency carries the information, right? So, and then what's the difference between these two? Now, what's the difference? I mean, what are the relations between these two, right? In order to see that, maybe let's first figure out, okay, so we know the frequency here, and we know the phase here, I mean, the angle here is this guy, right? Then what is the theta for FM, right? So what's the theta t for FM? Right, we know frequency here, right? And the relation between the frequency and the angle is the derivative of angle is frequency, right? Then if we want to know the angle, it means we need to do an integral of the frequency to get the angle, right? So that is basically what we do here. So we're doing integral. Let's assume the signal starts at 0, okay, instead of infinity. So basically, we do an integral of the frequency. So we denote that as alpha because we have a t here, right? This dummy variable is alpha, right? So that's basically what we got, and we can plug this in. So this basically equals to, so the first constant is easy, right? That's omega ct, right? But the second part here is the integral, right? So I have a kf, and then we do the integral of m alpha d alpha. Okay, so that's how what theta equals to, right? And then compare this guy and the theta here, right? And then you can see the difference, right? The first part is the same, right? That's carrier frequency. The second part, one is directly the information message, and the other one is the integral of it. Okay? Yeah, does that make sense? Yeah, this is basically the general concept, the concept of FM, right? So, yeah, now let's write down them together, right? Yeah, because we call them angle modulation, right? And the PM and the FM are just two special cases of angle modulation. So it turns out that we have a unified way to write these two together. Okay, let's see how we can do that. So the generalized angle modulation. Okay, so we can write down our modulated signal S of t equals to a, some constant, multiply cosine, right? What in the middle? So the carrier frequency is not changing, right? That's always omega ct. But for the later part, we can write in this way. So we can write that in terms of integral, but it's an integral in this form. No. Yeah, it's an integral in this form. Okay, and what is that? Yeah, it's a convolution, right? So basically, it's a convolution between M and H, right? Okay, very nice. And given this, so now we can see so here we can see we introduce kind of another function, so which is H, right? So basically, the modulation can be understood that as that, so our message signal passing through a linear system first, right? And then do the integral, and then do whatever, okay? And depends on how we design this, this linear system, and then we can recover the phase modulation or the frequency modulation, okay? For example, yeah, so basically, that is the LTI system. Right, so basically for the PM, let's see what do we have here. So for PM, so what is our HT? Right, can you see that? Just a constant, right? It's a constant multiply this. And then you do the integral to get it back. So what kind of operation is that? So by the way, right, so now, so yeah, it's like a constant multiply the input signal is definitely a linear system, right? And how can you represent it as a linear system? Or what is the impulse response of such a system? Let's say we don't have Kp there. It's just empty, right? And then when empty passing through, what kind of system? The output is still empty. Right? What is the identity operator as a system? Exactly, right? So if if it's kind of confusing, you can think that in the frequency domain, right? If you multiply a constant in the time domain, you multiply a constant in the frequency, right? If you multiply a constant in the frequency domain, right? Constant meaning that it's a line, flat line for all the frequency component, right? So the Fourier transform of that is a delta signal, right? So basically for this guy, this is Kp multiplied delta t, right? So that's how the system look like. How about for Fm? So what is h of t? Right? For Fm, it's just an integral, right? So it's just an integral, and then we can move this constant inside, right? It's m alpha multiplied constant to the integral. Compare this and that. So it basically means that h of t is just that constant, right? That's kf, right? Yes. Now it's not very complicated. Yeah. Don't be afraid to say it, right? It's very straightforward. Just kf, right? Because if you compare this and the other formula, the only difference here is that here is ht minus alpha. The other one is kf, right? Yeah.
So for the phase modulation, could you explain why, like, since it's Kp and then the derivative of m of t, why is the
So which one?
for phase modulation
For phase modulation?
oh, okay, never mind.
Which one?
The one.
Oh, no problem.
The angle of phase modulation.
So what's your question?
I think I figured it out.
Okay.
I was looking at the angle instead of the frequency instead of the angle.
Okay. Yeah, it's clear? Okay, any questions for this? Yeah, looks like easy, right? But you need to think a little bit. So otherwise, it's still quite confusing. Okay, yeah, this is how we deal with that. And the next, so yeah, those are the introduction part. So next, we're going to talk about the properties of angle modulation. Yeah. Yeah, for the property of the angle modulation, we're going to see the first property, which is about the power of the modulated signal. Okay, so here we're going to have an assumption. So assume our modulated signal, our carrier frequency is much larger than the bandwidth of the signal, right? So this is the bandwidth of MT. Okay, so consider this. What does that mean? So if the carrier frequency is way bigger than the bandwidth of the signal, so what does that mean physically?
They won't overlap when you modulate it.
Yeah, very nice. Yeah, yeah. What? Eric, right? Matthew. Who is Eric? Oh, you're Eric. Okay. Yeah. Sorry for that. Okay, yeah, what you mean is that if we do the modulation, let's say we do the AM modulation, right? Here is FC, right? Because this is B, then we can move this out completely without overlapping with the other one, right? Very nice. Okay, yeah, this is the meaning in the frequency domain. But what's the meaning in the time domain? Right, think about this. So basically for this FC, it's meaning how fast the carrier changing, right? And this B means how fast the signal is changing, right? Let's say for our modulated signal, yeah, we can just see here. Yeah, for our modulated signal, let's see, so this guy didn't change very much, right? So what does that mean? Right? Let's say, for example, for FM signal, so normally the frequency changing means that the signal may start from here, right? The magnitude is the same, right? And then so it may become smaller and then becomes faster again, right? So when the signal is not changing very fast, right, it basically means that within one period of this guy, it will still be a cosine. Does that make sense? Because the changing is very slow, right? Maybe you can see the change after like a 1,000 period, right? So this basically means that within one period, we can consider this guy as a cosine omega ct, right? Then we can use this approach to approximate the power of the signal, okay? So that's very easy to compute. Yeah, let's do the computation. Does that make sense, right? So basically, what we mean is that, so consider this as t square. Yeah, normally we use this notation, right? I sort of dropped it, but you know what I mean. So this, roughly speaking, it will equals to this guy. So I just use TC to denote the 1 over this, right? Which is the fundamental period of the carrier, right? And then remember the formula that we use to compute the power is as follows. So the signal look like the S of t like that, right? So basically, this equals to a square cosine something square, right? And dt. So this cosine something is where this condition is used, right? So as we said, so we have omega ct, but the added part is not changing very much. It basically means that within one period, the changing is a constant, right? It's just a constant c here, okay? And then this basically means that we want to compute the power of a cosine signal, right? And that equals to a squared over 2. Okay, so that's basically the power here. So what does it mean? So it means that the power is now changing, right? Because here we compute S of t is that it doesn't matter what value t is, right? So basically, the power of the signal is that is this guy. The power is now changing. So where we say that the power is a constant. Okay, so that's a very nice property of the angle modulation. So the power is not changing much. Okay, secondly, let's talk about another property of the angle modulation. So let's see whether the angle modulation is linear or nonlinear. Okay, how about that? Right, hopefully you still remember what does linear mean, right? So here, so a linear system basically means as follows. So here we use t to represent this transformation. Okay, or transform. So basically, TAM1T plus BM2T, that equals to ATM1T plus BTM2T, right? So this is the definition of a linear system. Hopefully, you still remember it, right? And give you such definition for a linear system. So what do you think? So is the angle modulation linear or not? Yeah, the only thing we need to do is that we need to compute this and compute that and see whether they are equal or not, right? So first, let's go back. Is the DSBSC signal linear or not? Let's remember. So for DSBSC, the modulated signal equals to our message signal multiplied cosine 2 pi of ct. Or we use omega, right? So yeah. Okay, so for this kind of system, is that linear or not? Right, because m is here, right? So it turns out it is a linear system, right? If you don't believe it, you just try this formula, and I wrote it down in my notes. You can take a look, right? But for this guy, for the angle modulation, right? So is that linear or not? Right? No? Yeah, so Any other answer? You just compute that very quickly in your head, right? Very nice. Yeah, let's try it, right? It's not linear, so that's the correct answer. So maybe we'll just try with the PM signal, okay? So basically, yeah, we denote as PM, as the I, as this guy, A cosine omega omega of t in general, okay, plus, yeah, let's do that omega c times t for easier. Omega ct times kpmi, so that will be easier to do, right? And then, yeah, we assume we did not have this notation, so PM1, 2, basically that is to compute this guy, right? So this equals to, yeah, so we need to do this. So it's A cosine omega ct plus kp, and then we have m1t, A m1t plus B m2t inside. Okay, so this is basically this part. And now let's see this part, right? So we write this part here. So this part equals to A times capital A cosine omega ct plus kp m1t. Yeah, it's not good enough. So. Huh? Well, this is even worse. How come? Okay, this is a bit better. So then we add this part, right? So B A cosine omega ct plus k. Oh no, sorry. Oh yeah, it's right. Right, exactly. M2t. Right. So now basically we're gonna see, I mean, whether this and that are equal. Right. Clearly it's not equal, right? Because we cannot take that directly out from a cosine, right? It's cosine operator. It's not linear. Okay, so this is not equal. So basically, we say angle modulation is nonlinear. It's not linear. Okay, great. Okay, so normally if a system is not linear, then there will be some bad things happen. Okay, but let's see whether this is the case or not. Okay, so yeah, let's take a look at the effect of nonlinearity. Okay, see what will happen here. So before taking a look at the angle modulation, let's take a look at the DSBSC signal. Okay. Right. So let's see if there's some. Yeah. Oh, by the way, so here this is nonlinearity doesn't mean the nonlinearity here, right? So this is a property of the system, right? So here the nonlinearity basically means that for example, the nonlinearity of the power amplifier, or the nonlinearity of the low pass filter, for example, right? So basically it means that if there's something happened on the modulated signal, right? So here is an example. So basically, if we consider, yeah, let's denote that in a simple way. So we consider DSB as C first, right? So it's easier to see whether it is good for the nonlinearity or not, right? So let's consider this as the follows. So basically, our DSB signal, so that equals to SC MT cosine omega ct, right? So this is a modulated signal. And now let's see y of t. So we assume when this guy passing through a system that is nonlinear. So one example is as this. So that will equal to A times S DSB of t plus B times S DSB, the third. Okay. Yeah, let's see, this is some output, right? So we'll pass through RS DSP signal through a kind of nonlinear system. Right, the output is y of t. Right, so this is what we consider. And let's assume this is the output, right? So I have a nonlinear term here. Okay, so this a times that is a linear term, but this is nonlinear term, right? So if we have that, let's see what is going to happen, right? Okay, so basically in this case, so let's plug this inside here. So we have a mt cosine omega ct and plus a b, and this is this cube, right? Cosine omega ct cube. Okay, so it's very hard to see anything from here, right? So we need to think in the frequency direction, right? But we can still do some modulation, although we need to think in that way. So basically, what we do is as follows. So basically, we have the hard part is that we have omega cosine omega ct cube, right? So this basically equals to cosine omega ct squared multiply another cosine omega ct, right? And for this part, we know how to deal with that, right? We just use 1 plus cosine 2 omega c divided by 2 to deal with that, right? So basically, now from here we can see the second term. So that will be equals to bm cubed times, maybe we'll divide by 2 here, 1 plus cosine 2 omega ct, and then times another omega ct. Okay, so that's very good. And you can see that we have a constant here, and then we have omega ct here, and then we have omega ct here, right? So basically, we could combine this term, right? So basically, together, yeah, we say you can write it here. So basically, here we have the first term amt, add, so this term, yeah, add this b over 2 m cubed t, and times cosine. Yeah. So basically, yeah, maybe I don't have time to do that. Maybe I'll do that next time. So basically, what we do here is that, so we have, yeah, maybe I can quickly do this. So now we have this cosine ct, right? We take it out, and then we have one term left, right? So basically, this guy is, so I have a cosine multiplied cosine, 2f omega ct plus cosine omega ct, right? For this term, so for this guy, so we can use the trig inequality to break it, right? So cosine multiplied cosine equals to what? So cosine alpha minus beta plus alpha plus beta, right? So basically, for this guy, will equals to cosine. We have a 1 over 2 in front. It's 2 cosine omega c minus omega ct. And then we plus half cosine 2 omega ct plus omega ct. Okay, and from here, so we get another, so this is equal to cosine omega ct, right? So here we have another omega ct, and we have a half here, and we have another half here, right? We add 1/4 on this side, right? So basically, we have 4 over 3 here, right? And then what is left over is this part, right? This part is half multiplied this half, right? Yeah, let me write it down, see whether it makes sense or not. So yeah, that is 1 over 4 mt3, and the cosine 3 omega ct, right? So that's basically what we got. Okay, and the point here is that, okay, so basically this part doesn't matter, right? We have 3 times omega c, right? So basically, we have more bandwidth for this guy, and we have this cube. Basically, this guy have a 3b of the bandwidth, right? So this is but we have a high frequency component. For this guy can be LPF, right? We use LPF to filter this out. So the problem is here. Okay, so basically, the problem is this guy, right? So we'll use some amplitude detection to detect this. So this is a distortion. Okay, so which is not good. Okay, the point of this example is to show you that for DSBSC signal, if we have a nonlinearity of the system, so it's not good for that. Okay, so in the next lecture, we're going to see for the angle modulation, FM, so we can deal with that. Okay, it's not a problem. Okay, yeah.